Okay, so we're going to continue with the definite integral properties and proofs from last week, Thursday. There's 3 of them that we didn't finish during that Thursday lecture. We're going to finish that now. Then there are 2 more that we need to go through. One of them we'll go through the proof as we did for the others. The other one we will not be going through the proof, and that means it will not be tested. Yeah. If we don't do the proof, or I don't say the proof is for homework, then it is not testable. Okay. And then we've got some questions using the properties. Okay, so last time I think we finished off with number 8. Okay, so the others are set for homework, and then it was 8, 9, and 10, that was for classwork. Okay, so property number 8, just to give you a refresher. Okay, again, please make sure you have the list of these properties. Okay. Yeah. Number 5. That was from Thursday, wasn't it? Yeah, it's up here. So the even one we did in class. There's the rest of it there. And then the odd one that was for homework. Yeah. The fact that you asked that means you didn't look at the lecture notes. Yeah. No, not written. The ones that are uploaded. There's the full proof there already there. So you shouldn't be asking that. Okay. Let's get back to this one. Okay, please, even if you write out everything during the lecture, those PDF of the lecture notes are still very important, right? I could add something, I could make a note for the test, right? If you miss it, right, it's not my problem. You didn't read the notes. Okay, so property number 8, if f is greater than or equal to 0 on the closed interval AB, then the integral from a to b, f of x dx, is also greater than or equal to 0. And I said last time, we can do exactly the same thing for f less than or equal to 0. So we just swap the less than or equal to on that side, and then the same on the other. So the proof's exactly the same, you're just swapping the sign. Okay, so let's go through the proof. So basically, we're trying to show if the function is positive, then the height of each rectangle is positive. And if that's positive, well, then the area is also positive. Okay, straightforward. Okay, so we know that the function is always positive on AB. So that means f of x is greater than or equal to 0 for all x in AB. Okay, so we know it works for all x. So that means it also works for any x sub I that we pick. Remember, for the rectangles, we pick any xi from a to b, that will also make f positive. Okay, remember xi, that was that base of the rectangle that we picked. So if the function's positive, then the function will also be positive for any xi. Now, what we can do is multiply both sides of this inequality by delta x. It's positive, so it won't change the sign. And on the right-hand side there, it's 0, so it will stay 0. So let's multiply by delta x. And the inequality stays the same because the delta x is positive, right? B minus a over n is positive. So that individual term there is positive. If we sum over I, it will still be positive because each of the individual terms is positive. So we're going to do the sum from I equals 1 to n of xi delta x, and that will still be positive because each term in the sum is positive, so the whole sum is positive again. So each term is positive. So the sum is positive. And if the sum is positive for any capital N at the top there, then it is true that the limit of the sum is also positive. Right? Because that sum up to N there is always positive for any capital N. So if we take the limit, it's still positive. Good. And finally, what we built up there on the left-hand side is just the definite integral. Very simple. Right. Any questions for this one? All good. Okay. And again, we could just swap the inequality and all of the reasons remain exactly the same, but instead of positive, you say negative. It works exactly the same. Then there was number 9 that we didn't get to. If f is greater than or equal to g on the closed interval AB. Okay, so f is larger than g, then the area under f is larger than the area under g. Right, again, very simple. If the height is larger, then the area under that curve will also be larger. Okay, now, proving this, we can go through the whole long process of what we did above, okay, but we want to avoid all of that work, so we're going to do something simpler. Let's start there on the right-hand side, okay, with that inequality. So we're just thinking about making this simpler. Okay, so it's just an idea of trying to make this simpler. Let's look at that right side and see what we can do to make it look like something we already proved before. Okay, so we don't want to start all the way from the beginning. We want to use what we've done before to prove this over here. Okay, so we have the integral from a to b, f of x dx is greater than or equal to the integral from a to b, g of x dx. Okay, let's take everything over to one side. Again, this is just thinking about what we're going to do. So we're going to take everything over to one side here. We get the integral from a to b, f of x dx, minus the integral from a to b, g of x dx is greater than or equal to 0. Now, we've seen something like this before. So we have two integrals with the same bounds, different integrands. What can we do with this difference? Well, yeah, we can use property 1. We can group it together under one integral. Yeah. Again, this is all just thinking about what we're going to do. Now, this inside part there, I'm going to call that h. So it's a new function, which is the difference between the two. And here, this is a new function, so I better say what it is. Okay. So what do we have now? We have that the integral from a to b of this new function h is positive. Now, what does that look like? It looks exactly like what we had over here. So we have if f is greater than or equal to 0, then the integral is also greater than or equal to 0. So let's define this f, which will be our h. We're going to call that h there. And then just use what we have before. So a little bit of rewriting, and we just use what we have. Okay, so proof. So in order to use what we had before, we need some function f that's always positive. Well, we've got this h here, which is f minus g. Is that always positive? Yes. F is greater than g. So f minus g is greater than 0. So yes, that is positive. So we're going to let h of x be f of x minus g of x. Now, this has to be positive for us to use the proof, and it is because we know f is greater than g. Right, that was given to us, f is greater than g. Now, since h is a positive function, we know that the integral will also be positive, so let's do the integral. So from 8, we get that the integral is also positive. Okay. Now we can substitute what h is. And we're just working backwards from what we had earlier when we were thinking. Okay. Now we can use property 1 to split up that integral. And finally, we can take that negative term over to the other side, and we're done. So instead of going right back to the beginning with the definition, the limit definition, we just use property 1, we use property 8, and we can prove this. Okay. So we don't need to go right back to the beginning every single time. You have 10 properties. You can use the properties to prove other properties. Okay. But if you did want to go back right to the beginning with the limit definition, that's fine as well. It works, but this is a lot shorter. All right. Any questions for this one? You're all good. Okay, and we're going to do a similar thing for number 10. Instead of going right back to the beginning with the limit definition, we're going to use several properties we had before. Okay, so what was number 10? If little m is less than or equal to f less than or equal to capital M, so we have a bounded function on AB, then we had the following inequality. And we want to prove this. Now, again, we don't want to start right from the beginning. We want to use what we have already done. So we're going to split this up into two parts. We're going to look at the left integral with the little m, and then we're going to look at the right integral with capital M, and then just put it together at the end. Okay, so let's look at the left inequality. Okay. So what do we have for the left inequality? So starting from the beginning there, we know that little m is less than or equal to f. So that's our starting inequality. What we want to do is get to that left inequality with the integral. So how can we get from this to what we want? Maybe some points will motivate you. Yeah.
You can use FX using this one, just use some inequalities.
Yeah. Yeah.
Since it should be the integral important behind and really safe and it will be
Yeah. Good. Very good. Can get some points for that. Nice explanation as well. One sec. I just took your student over there. Good. So we're going to treat this as a function inequality that we just proved over here. Okay. If f is greater than or equal to g, then we have that with the integrals. Now, over here, this g, we could just take as the constant function, little m. Okay. It doesn't have to be some function that changes with x. This m over here, we just take as a constant function, and then apply the property. So using the property 9 that we proved above, we have that the integral from a to b m dx is less than or equal to the integral from a to b f of x dx. Right. Here, the function g that we had before is now just this constant m. Okay, now we can use a few more properties. M is a constant, so we can take it outside of the definite integral. Okay, that was one of the properties. Right, we had the constant times f, the constant can come out. Next, the integral from a to b dx. Remember, there was that hidden 1 there. That was just b minus a. That was another property. Yeah. And that's exactly what we need for this left side of the inequality. Now we're going to do exactly the same thing for the right side. Okay, but instead of the little m, it's going to be the capital M. So we're going to have f of x is less than or equal to capital M. For all x in AB. Right, again, m we can just treat as a constant function. So if f is less than m, then the integral of f is less than the integral of m. Again, that was property 9. Okay, but same as before, m is a constant, we can take it out. Okay, and then the other property, remember there's that 1 there, so the integral a to b dx, that's just b minus a. Okay, and that's exactly what we needed for that right side. So we have a less than b less than c. We can just put both parts together. So that was from part 1, right? A less than b, and then from part 2, b less than c. So this is just less than or equal to what we had before. Okay. So we just split it up into 2 inequalities and then put them together at the end. Any questions for this one? Oh. Okay, so we've got two more to go through, property 11 and 12. 11, we'll do the proof, okay? Whenever we do the proof, it's testable. And then property 12, we will not do the proof. So you still need to know the property, but you do not need to know the proof. Okay, it's a bit too much to go through. Okay, so we're just continuing the list from last time. So number 11. The absolute value of the integral from a to b, f of x dx, is less than or equal to the integral from a to b, absolute value f of x dx. Okay. And we want to prove this. So if we have the absolute value of the integral, the absolute value can go inside. So we have the absolute value of f, but the equality now becomes an inequality. Okay, so an absolute value goes inside. We need to make it an inequality. And then we end up with absolute value of f on the inside. Okay, how are we going to prove this? Are you familiar with the triangle inequality? No. Okay, let's go through that. So remember that this integral is secretly a sum, right? So the integral from a to b was the limit of a Riemann sum. So let's just do a little bit of side working here. Okay, since you don't know the triangle inequality, we'll do some extra working here. So if we have the absolute value of a plus b plus c plus whatever, the triangle inequality says that this is less than or equal to the absolute value of a plus the absolute value of b plus absolute value of c, and so on. Now, how does this help us? Well, for the triangle inequality we have there, it's a sum a plus b plus c. Okay? And then on the right side, absolute value of a plus absolute value of b plus absolute value of c, and so on. Now, for our problem, it's not a sum, it's an integral. But the integral is just the limit of a sum. Okay. So what we're going to do is treat both sides as summations without the limit, use the triangle inequality on just the sum, and then take the limits at the end. Yeah, that's the idea. So the idea, using the triangle inequality, which we still need to prove, but it's over there. Using the triangle inequality, we can prove the inequality for sums. And then take the limit. So we'll prove it for a Riemann sum. Then when we take the limit, then we've proven it for a Riemann definite integral. Okay. And again, we can do this because we know the definite integral is just the limit of a sum. So if it works for a sum, it might then work for the limit of a sum. But we need to prove that. Okay, but before we get to that, let's do the triangle inequality. Okay, so we're going to do it for just a plus b on both sides, but it extends to any sum. Pen. Did you not cover that in high school? Triangle inequality. Okay, that's fine. Oh. So proof of triangle inequality. Okay, so again, we'll prove it for just a plus b, but it continues on. So you can do a plus b plus c plus whatever. Okay, so there's a few things that we need before that. So if I have some a, I think we can all agree that a is less than or equal to the absolute value of a. Okay? Because if a is positive, then it's just equal to. If a is negative, well, the right-hand side is positive, so the equality stays. Okay, so we all agree. Then, if I square both sides, we can still keep the inequality. Okay? I can do the same thing for b. So if b is less than or equal to the absolute value of b, I can square both sides, the equality stays. Okay. In fact, it becomes an equality, but we don't want that. The inequality stays there. And finally, from number 1 and number 2 there, if a is less than or equal to the absolute value of a, and b is less than or equal to the absolute value of b, I can take the product of the two. So AB is less than or equal to the absolute value of AB. Yeah, we're just taking the products there. So we've got 3 things. Okay, we're going to need those. Okay, so this doesn't come with any proof. Proof by it's obvious, right? Now we're going to consider 2 equations. The first one is the absolute value of A plus the absolute value of B squared. Okay, so we take A plus B, the absolute values, and square the whole thing. So what's this going to be? It will be the square of the first term plus the square of the second term plus 2 times the first term times the second term. Yep. Very easy so far. Now we're going to do exactly the same thing, but without the absolute values, with just A and B. Okay, same thing. It will be the square of the first term, square of the second term, and twice the product. Okay, so let's call this equation 4 and 5 to continue with the list. Now let's look at equation 4 and 5 with equations 1, 2, and 3 in mind. So the first term from equation 4 is the absolute value of a squared, and the first term from equation 5 is a squared. What can you tell me about the relationship between those two? Right? The second one is smaller, right? From number 1, right? Second one smaller. Okay, let's look at b squared for equations 4 and 5. We have absolute value of b squared and b squared. The second one smaller. Let's look at the third one. We have 2 times absolute value of a times b and 2ab. Right? From equation 3 there. The third one there is smaller. So each one is smaller than the equation 4. Therefore, the second one here must be smaller than the first one, right? Because each one was smaller, so it must be smaller. Okay. So we end up with this. Now, what we're going to do is drop the squares on both sides. Okay? But we know that right-hand side there is always positive, right? Because of the absolute value. but this left-hand side might not be. Right? Could be negative. So when we drop the squares, it needs to be the absolute value of that. Right? It's the same thing as root x squared is absolute value of x, right? So we're going to drop the squares on both sides, and we end up with this. Again, think root x squared. Okay. So we took the roots on both sides, but we need to put the absolute value back there. Okay, and that's it. Right? Absolute value of a plus b is less than or equal to absolute value of a plus the absolute value of b. And you can extend this to any sum. So we've done it for a plus b. You can do exactly the same thing for a plus b plus c, and so on. So we can extend this to any finite sum. So on the one side, we're going to put a sum, I equals 1 to n, a sub I, whatever that might be. So a1, a2, a3, and so on. This is less than or equal to the sum, I equals 1 to n, absolute value, a sub I. Yeah, so we proved it for 2 terms, but that's equivalent to proving it for any finite sum. Okay. And I think this kind of gives it away what we're trying to do. So once we have the sum, we just do the limit of the sum, and that's the definite integral. Okay, so back to the proof. So all of this was the side working because you didn't know the triangle inequality. So now we get to the main proof. Okay, so somehow we want to turn these sums over here into these integrals over here. So we're going to start on the left side and end up on the right side using that inequality. Okay, so absolute value, integral a to b, f of x dx is equal to, right? When we don't know where to start, we start with the definition. So this will be absolute value of the limit of a Riemann sum. Now, the triangle inequality, as we had over there, works for finite sums from 1 to n, that we know it works. Over here, we have an infinite sum because n is going to infinity. So inside the absolute value, we don't want the limit there. Yeah, we just want the normal sum. So we want to take the limit outside of the absolute value. What tells us that that is okay to do? Remember, proofs are steps and reasons. So we've got a step we want to do. We want to take the limit out. Now we need the reason. Why can we do that? Again, extra plus 3 points. Right, we've got the step. Now we need the reason. Think back to limits. Yep.
Thinking, since it is value,
Yeah.
the definition is a definition for then we just take out the
Yeah. What do we call that?
um,
It's not just left equals right. There's a word for the 3 things. That was one of it. But there's a word for all of that. Continuity, exactly. Very good. The absolute value is continuous. The limit can come out. Good. Where's that page? Extra. Did I mention the points carry over?
Yes.
I did. Okay. So if you get 100, whatever's left over goes to the next one. If you get 100 still, carries over up to the class test. Right. Whatever's left over just goes into the class test. Good. the absolute value function there is continuous, so the limit can come out. Reason, so that was the step. Reason, absolute value is continuous. Okay, and that goes back to what I said in the Thursday lecture about all the definitions we've done. Right? Continuity, limits, differentiability, it all comes up. So maybe the question won't be show it's continuous, but it might be a reason that you need for a given step, right? It's continuous. Okay, good. Now this is almost what we want. We know that it works for finite sums like this, but there's this delta x in the way here. What can we do with that? There's a delta x in the sum. We want that to be outside. What can we do? Yeah? No, we don't need to do that. You can, but it's not needed. Okay, remember what we're trying to do. We're trying to get to this sum over here, and then the sum on the right here, we want to get to this integral over here. But notice this dx is not in the absolute value. So the delta x that we have in the absolute value must become this dx over here. So what can we do? It's very, very simple. Like you said, b minus a over n. What is that? Yeah? The constant. More specifically, because we're dealing with this absolute value stuff. So when does the absolute value do nothing to the number? I can't give you half a point though. Must be full answer. Anyone else want to use his answer? That was a half answer. If someone gives a full answer, they get the points. Sorry? Positive constant. Yeah. We can take it outside the absolute value, and the absolute value won't do anything to it. Good. Let's pass that down. Good. So it's a positive constant. If we take it outside the absolute value, nothing happens. It's positive. So this is going to be equal to the limit n goes to infinity, the sum I equals 1 to n, f of xi, delta x. If delta x was not positive, or we didn't know what it was, then we would need absolute values on it as well. But we know it's positive, so the absolute values do nothing. We can just write it like that. Yeah. So reason, absolute value of delta x is a positive constant. Right? We need those two properties. It must be positive and it must be a constant so that we can just take it out like that. Okay, good. Now what? So these have all been equalities down here. But remember what we want? We want to get to this. So what can we do? Yeah, another 3 points. Right. Just imagine you're in a test. You got step 1, step 2, step 3. What do we do next with what's given? Everything's there. There's nothing new we need to do. Right? For the proof, you have everything already on the page. So if you say something that's not on the page, that's not right. Everything's there. Yeah.
Didn't we see before when triangle inequality that whether the absolute value of the sum of n ai
Yeah.
I think is the less so pushing the sum of n with the absolute value of ai only.
Yeah, exactly. We've got a finite sum in an absolute value. We can use the triangle inequality. Good. You get your points. Everything's on the page, right? You just scroll up a bit. There's the triangle inequality. There's nothing new that we're doing.
I just like those.
Yeah, over here. This bit. Right. It works for finite sums. We have finite sums, so let's use the triangle inequality. So this is now going to be less than or equal to the limit n goes to infinity. Now the sum goes on the outside, and the absolute value jumps in, becomes an inequality. Okay. What's this now? So just as written, whatever I written down. Yeah. Yep. Definite integral of what? Yeah, it's a definite integral, but of what? Of f, of p, q, x squared. Of?
Absolute.
Not of f,
Absolute.
of absolute value. You got the page. Just put a times 2 there. Yeah, so this limit of the sum is just the definite integral with absolute value of f. Right? The limit of the sum becomes the integral, the delta x becomes the dx, and whatever we're summing becomes the integrand. Right. Again, nothing new. Everything is just on the page. You just need to rename some things. All right. Any questions for this one? Okay. And then the last one. Again, we're not going to do the proof, but you do need to know the property. Number 12. This is the Cauchy-Schwarz inequality. Yep. So again, there's no proof for this one, but you still need to know it. So here we have the integral from a to b, f of x times g of x. So here, remember those properties we had before? We had the sum of f and g, the difference of f and g, some constant times f, all of that. And now we have a product. Now, we're going to take the whole thing squared, and this is going to be less than or equal to the integral from a to b of f just by itself squared, and then the integral a to b of g by itself there squared. So f squared g squared. Okay, there's a lot of squares here. Sorry, the square's on the inside there. So it's the integral of f squared, okay, by itself as an integral, and then the integral of g squared by itself. Okay, so we can split this integral of the product into two parts, okay, there, but it's not an equality, it's an inequality. Yeah, so just keep that in mind. Okay, then a few homework problems for you to try. So note that all of these have been with inequalities. Okay, so the three properties we had earlier, And this one here, it's all with inequalities. So these homework problems are prove the following inequalities. You can't be that sleepy. Right? You still have homework to do. Okay. Prove the following inequalities. Right. And since you're proving an inequality, you're going to be using those properties we had earlier. So when f is positive, when f is less than g, this one over here, the triangle inequality, and the Cauchy-Schwarz, those are all inequalities. Okay, so number 1, 2 is less than or equal to the integral from -1 to 1, root 1 plus x squared dx is less than or equal to 2 root 2. Okay. And you can think about this, look at what's given, and it's going to be one of those inequality proofs. Which one? 10. Yeah, good. Okay, so someone's ahead. Yeah, this will be property 10. But yeah, you're going to have to look through the properties, see what fits, and then you can work it out from left-hand side to right-hand side. So number 2, we have pi over 12 is less than or equal to the integral from pi over 6 to pi over 3 of sine x dx, less than or equal to root 3 pi over 12. Okay, again, you can think about which property that's going to be. Number 3, integral from 0 to pi over 2 x sine x dx is less than or equal to pi squared over 8. You can actually do this 2 different ways. Okay. So you can think about that. Remember, if this is in the test and there's 2 ways to do it, you get the marks for both. Okay. So if this is like a 4-mark question and you can do it using, let's say, property 7 and property 11 or whatever, if you do it both ways, you get 8 out of 4. Yep. And then finally, number 4, we have the integral from -1 to 1, root 1 plus x to the 4 is less than or equal to 2 root 2. Okay. This one is a combination of properties that you need. I'll give you a hint. Notice we have x to the 4, and we're going from -1 to 1. There's something we can do with that. Okay. Any questions for the homework? Okay, good. Remember, tomorrow is also a Monday. Okay, so please don't follow your Tuesday timetable. It's whatever you had today, same thing tomorrow. Okay, including the maths. Can't hear you. No, yeah, we'll have a quiz. No, the quiz is on what we did last week. Right? We finished all of that stuff. That's the quiz for this week. Yeah, this inequality stuff will not be on the quiz. It's the properties we did last week. And the limit definition of the definite integral. Okay. Any other questions? Okay, see you tomorrow.